So it might seem kind of strange to go from chapter 16 all the way back to chapter 8, and in fact a lot of chemistry teachers and chemistry books teach this chapter in the first semester as you're doing some other things with the periodic table. I actually choose to do this chapter at the end because we can do more with it. A lot of the terminology and things like that make a little bit better sense, and since we just talked about solutions, now we can take a look at, a little bit more in depth as to what will actually form a solution and so on. So there's a lot of different applications with it, and so we're going to start with a review from first semester, and it's not that bad. Here are 7 different elements. We're taking a look at how do we actually draw those out in terms of Lewis dot diagrams, and also interpret what are called valence electrons, and you're going to see how this pieces together. So I've got the periodic table here. We just kind of take a look. Remember, this is a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and so on. Now remember, what Lewis dot diagrams are showing the electrons in the highest energy level. We refer to those as valence electrons. Lewis dot is how we actually show them, and valence electrons is actually counting them up, and then we can figure out something called oxidation numbers from that as well. So those 3 terms we're just going to bring back for a moment. Oxidation number is another one of them, and that's going to go into how do we write actually compounds and so on. So Lewis dot diagram, if we go back and we take a look at an example like number 2, which is carbon, you see that we have 1s2, 2s2, and 2p2. So you don't have to write all the electron configurations again. I'm just kind of showing you how this is done, and we take a look at the Lewis dot diagram, which is the S's and P's of the highest energy level. So we take a look. Energy level 2 is the highest energy level, and so we have the element C, which stands for everything that's underneath the highest energy level. We have 2 S's, and then we have 2 P's. Remember how these fill. We have 1 and then 2. So let's take a look at another one. For example, let's look at iodine. Okay, iodine is way down here, so it goes 1s2, 2s2, blah blah blah, and it goes all the way down to 5s2, 4d10. So we keep on going, 5s2, 4d10, 5p5. And so to do iodine, remember it's the S's and P's, the highest energy level. We have the S's, we have 2 S's, and we have 5 P's. 1, 2, 3, 4, and 5. So that's what we're doing when we fill out the Lewis dot diagram. We see that in carbon there's 4 valence electrons. In iodine we would then have a grand total of 7. Now remember, ultimately what we want to form a compound, we want to ultimately have 8 total. Okay, that's a full octet. So to fill out, we would have an oxidation number. It's looking to fill out 1, 2, 3, and 4 more spots. So it would have either a +4 or a -4 charge if it's going to become an ion, because it's just as easy to gain 4 electrons as it is to lose. Now you take a look at iodine. Iodine has 7 total valence electrons, and it has 1 more spot right there to fill. So it would, because electrons are negative, it would have a -1 charge. This is just a reminder of why we have charges, and then we're going to see in this chapter how they form together to form a compound. Now, Vesper theory is taking a look at how do we draw these things. It's more of a geometry of the chemistry behind it. We're going to look at sizes, we're going to look at polarities, we're going to look at a whole bunch of different things, but it stands for the valence shell electronegative pair repulsion theory. So the valence shell electron pair repulsion theory, and it's just looking at what are the laws that govern if something is going to form a solution, the charges that are going to be associated with the individuals to come together, what ratios they come together, polarities if they're going to form a solution, and so on. So what I'd like you to do to start out with is I want you all to finish up with these specific elements, and then I'm going to bring together another video that shows, okay, when we're forming a compound between, for example, calcium and chlorine, how does that actually look? And then we can interpret some other things. So take a moment and do those other ones just to refresh how all of this works in terms of the periodic table and figuring out these items, and then we'll check back in and take a look at the assignment.